In our previous lessons, we defined pointer variables, and we also saw how to operate upon pointer variables, how to work with pointer variables in C or C++ program. But we did not really talk about the real use cases of pointer variables, in what scenarios we may want to use pointer variables. So in this lesson, we will talk about one of the use cases of pointer variables, and the use case is using pointers as function arguments, and we also term this as call by reference. So let's discuss a scenario. Albert is a beginner programmer, and he has recently learned about the concept user-defined functions. Now he tries to apply this concept, and he writes a simple C program like this. What he is trying to achieve here is that he has an integer variable declared and initialized in the main method, and he wants to increment the value in this variable by 1. So instead of writing something like a plus plus or a equal to a plus 1, instead of writing a statement like this, he writes a function increment that will take an integer a as argument, and inside this function he is writing a statement like a is equal to a plus 1. He calls this function increment from the main method, passing a as argument, and then he prints the value of a. Now what he is expecting here is that the value of a will be incremented to 11, and hence the print statement will print a equal 11. But when he runs the program, the output of the print statement is a equal 10. Now Albert does not understand why this is happening. He has declared a variable a, and then he has initialized this variable to 10, and then he is passing the same a to the function increment, and the same a is being incremented by 1 in this function. So why the value of a being printed is not 11? Why is it 10? Now what Albert does not understand well, or what he probably forgot, is that whenever we declare a variable inside a function, then we call that variable a local variable, because as such, just using the variable name, we can access that variable only inside the same function in which we have declared the variable. So these two a, this a in the function increment and this a in the function main, are actually not the same a. The a in the function increment is another a. When main calls the method increment and passes this a as argument to the function, then only the value of a is copied to this another a, which is another variable local to the increment function. So what I'll do is I'll do a couple of modifications in this code to show you a better picture. I will write two print statements in this code. First print statement in the increment method, something like this. Address of variable a in increment is, and as we know, if we put ampersand operator in front of the variable name, then we get the address of that variable. And I'll comment out this print, and I'll write one more print in the main method like this, and here I print that address of variable a in main is ampersand a. Let us now run this and see what happens. Let me also put an end of line after we print the statement, and the output is address of variable a in increment method is printed as 4454460, and in main it is equal to 4454660. These two look similar, but they're not the same. One is having 4460 in the end and another is having 4660. What the values are is not important. What the addresses are is not important. What's important is that these addresses are different. If the a in main method and the a in increment method were same, these two addresses would have been same. To understand this even better, we will try to understand how things happen in computer's memory when a program executes. When a program or an application is started, then the computer sets aside, the machine sets aside or reserves some amount of memory for the execution of this program. The memory that is set aside for the application is typically divided into these four parts that we are showing here. One part of memory is allocated to store the various instructions in the program. The computer needs to keep all these instructions in the memory, these instructions that we have in the program, like increment or declare these variables, all these sequential instructions. One part of the allocated memory is for static or global variables. If we do not declare a variable inside a function in C++ or C, then it is a global variable. Now, global variables can be accessed and modified anywhere in the program, unlike local variables, which can be accessed and modified within a particular function or within a particular code block. Now, the third part of the application's memory is called as stack, and this is really important. This is where all the local variables go, and we will mostly be talking about stack in this lesson. And the fourth part is heap, and we will come to this later in our forthcoming lessons. Of these four segments of the allocated memory, the text segment, the global variable segment, and the stack segment, these three are fixed and they are decided when the program starts executing. The application, however, can keep asking for more memory for its heap segment during its execution only. We will cover all of these things in detail in our forthcoming lessons. Please do not get scared by these terms. Let us now see what happens when a program executes. Let us say this is our computer's overall memory, the RAM, and as we know, each byte in the memory is addressable. So let's say the memory allocated for our program is from address 200 to 800, and these are the various segments of our application's memory. And of this, let's say address 300 to 600 is allocated for stack. Now there is more memory, of course, in the RAM after address 800 and before address 200. Okay, so from 200 to 800, this part of the memory is assigned for our program. Let's say this C program that we have in the left. Now, when a function is invoked, like when the program starts, the main method is initially invoked. All the information about the method call, like its parameters, all the local variables, the calling function to which it should return, the current instruction at which it is executing, all this information is stored in the stack. So we will take out from the stack some part for the main method and create a unit which we call stack frame. Each function will have a stack frame. Now we have a variable a. Now memory is allocated for a from this stack frame and the value of a is 10. Now the main method calls increment function. What happens when main method calls increment is that the machine says that, hey, I will stop your execution for some time. I will stop at this particular instruction. Let me go ahead and finish this method increment, and then I'll come back to the main method once I'm done with increment. Now another stack frame is allocated for the increment method, and the parameters in increment method, like we have a parameter a, so fresh local variables are created corresponding to these parameters, and whatever values have been passed are copied to these variables, these parameters. Now when we say a is equal to a plus 1 here in this statement, then what happens that this a, which is local to the increment function in this particular stack frame, this a is incremented. We cannot access a variable outside its stack frame, and now increment finishes. When increment finishes, the control returns to the main method, and what the machine does is it clears the stack frame that was allocated for increment, and main method resumes again. So main method was paused at this particular instruction increment. So lifetime of a local variable is till the time the function is executing. Now the next statement in main method is a call to the function printf. Printf is not a user defined function, it is a library function. The state of execution of main method is kind of paused and printf is executing now. We often call this particular structure call stack or function call stack. Whatever function is at the top of this stack is executing, and remember this stack is fixed in size. So if you have a scenario where one function keeps calling another function indefinitely, like in the case of indefinite recursion, then the memory of this stack will overflow and our program will crash. Okay, but that is not relevant for this scenario. So now you must be getting a picture of what happens when one function calls another function. This A is in the stack frame of the main method. Main is our calling function and increment is our called function. When we call a function, in the calling function, the argument is also known as actual argument. And in the called function, the argument is known as formal argument. All that happens is the actual argument is actually mapped to a formal argument. So when this function call happens, A is mapped to A as an actual argument is mapped to another A, which is a formal argument. Instead of A, if we were having an X here, so we would have written something like int X as is the argument and X is X plus 1, then A would have been mapped to X. So the value of A will be copied to the variable X. Now when we make such a function call where we basically have one variable being mapped to another variable, the value in one variable copied to another variable, then such a function call is also called as call by value. So this is what Albert was doing, making a call by value, and that's why he was not able to get the desired result. But can we get the result that Albert wanted to have? Albert wanted to use this variable A, which is local to the main method, inside the increment function. Can we really do so? Well, yes, we can do so if we use pointers as function arguments. Let us now look at this code, and I'm drawing only the stack here so that I'm able to show the simulation of program execution neatly. Now what we are doing here is that we do not have an argument which is integer in this function increment. We have an argument which is pointer to integer, and pointer to integer, as we know, it will store the address of an integer. So now what we are doing is that in the increment function we are passing the address of A. So when the program will start executing, the main method will be invoked first. Let's say this is the stack frame of the main method. Let's say 300 to 350, this address is the stack frame of main method, and there would be a local variable A in this main method. Let's say the address at which A is stored is 308. This may not be in proportion, but still, let's say this is how it is stored. Now when main method calls increment, then a local variable corresponding to the parameter P is created, and this is a pointer to integer, and the value that is passed to this particular function, the value that gets stored in this particular, sorry, it's not a function, it's a variable, the value that gets copied or stored in this particular variable would be 308, the address of A. So P is pointing to A. Now in this statement here, when we say asterisk P, we dereference this address. So we are saying here that asterisk P is value at address stored in P. So we say that increment the value stored at address P by 1. The value stored at address 308 gets incremented by 1. So A is now 11. So now when increment finishes and we come back to the main method and the next line gets executed, which is the print statement, then A is now 11. If you run this program, then what gets printed is A equal 11. Such a function call in which instead of passing the value of a variable, we pass the address of the variable so that we have a reference to the variable and we can dereference it and perform some operations is called call by reference. So if we use pointers as functions arguments, then we are using call by reference. Call by reference can save us a lot of memory, because instead of creating a copy of a large and complex data type, if we just use a reference to it, and using a reference will also cost us some memory, but very small amount of memory, then we are saved from creating a new copy of a complex data type. In the coming lessons, we will see more of the layout of applications memory and what all things we can do using pointers. So thanks for watching.